Hello, and welcome to Discussion 3 for CS61B. Today we're going to be talking about linked lists and arrays. First things first, let's get some announcements out of the way. Project 1A has been released. It's due next Monday. We have exam prep sections now, and there will be video walkthroughs released for those as well. So if you want some extra practice on exam level questions, feel free to check that out. Lab 2 checkoff is due this Friday if you did not get it done during lab last week. We have released this thing called Gitbugs. You can read more about it on Ed or on the website. But basically this gives us a better way to look through your code if you're having an issue, because screenshots are not very useful and debugging in office hours takes a really long time. And on that thread, we're not going to be offering debugging help anymore in office hours. So for office hours, you should mostly stick to conceptual questions, and if your code's not working, submit a Gitbug. Okay, let's get into some content review. First, let's do a review on arrays. Like we mentioned last week, arrays are objects that are immutable or unchangeable in size. So once you've created an array, you cannot make it have less or more elements than it did when you created it. Second of all, arrays are very strict in what type they take. So if you create some sort of int array, every object you put inside R has to be an integer. You can't put a string in there, you can't put a boolean in there, whatever. It has to be an integer. So why do we use arrays? Well, first of all, arrays are fast, because unlike Python arrays or linked lists, Java knows in memory where each element is. So if you think about how a linked list might be stored, it's very modular, right? So maybe if you have your computer memory, you have like the first part of the linked list here, and then like the second part down here maybe, and it points there, the third part over there. And so your computer has to physically follow these arrows to get to that place, to find the third element in memory. For arrays, because we initialize them with the size at the beginning, all of these elements are stored in a single row in one line. And so all Java needs to do is, oh, you want the third item? Okay, so let's say this is like memory space 32. Now let's just add 1, add 1, add 1. So if you just add 3, it'll jump you to the third element. So Java arrays are a lot faster, basically. Second of all, Java arrays are a lot safer. Because the size is so predetermined, it's easier to catch errors before you actually run your code, which is super helpful if your code is very long and it might take a while to hit a problem area. Of course, this won't stop all errors. You still might get a null pointer exception or an array index out of bounds exception if you're using a while loop, for instance, but it can prevent a lot of them before they occur. Now let's go to more on linked lists compared to last week. So since last week, we learned about doubly linked lists versus singly linked lists. Just for a quick review, single linked lists contain one value and one pointer to like the next item. So they link in one direction. Doubly linked lists have pointers to both the previous item and the next item. So it would look more like this, with the value in the middle, your previous, your next, and they point in both ways. The goal of having a linked list object versus just messing around with individual int nodes is that if you have a linked list object, you don't have to, every time you want to do an operation on your linked list, you don't want to have to mess around with individual int nodes, because that's just a recipe for making more mistakes. So the goal is to use your linked list object in order to abstract away all those things like adding and getting and putting and whatever. Also, what we've learned in lectures since last week is about sentinel nodes. And so sentinel nodes are one of those features of having a linked list object as opposed to having a bunch of individual int nodes. And so what a sentinel node is a node, like a pseudo node of sorts, that doesn't contain any value, but it points to the first item. Or if it's a doubly linked list, it points to the first and the last item. And this basically means that the user has no way to access the int nodes directly at all. You have to go through the linked list class, and the linked list class goes through their Sentinel node. It's just another layer of protection. Okay, so the big question, why do we use linked lists? Now, linked lists are fast in a different reason than arrays, right? Because arrays are fast for getting mostly. Getting, changing the value at a specific index, things like that. Linked lists are a lot faster if you want to insert or remove. Even though they have to travel through the entire linked list, unlike for arrays, they don't have to physically copy over the linked list into a larger space. And so because of that, inserting and removing is a lot faster in a linked list. Also, linked lists are flexible. Like I said, you can change the size of a linked list without much work. Because it's a sequence of nodes, and you can just change these pointers to point toward something else if you want to. So, in practice, there are times when linked lists are more useful, there are times when arrays are more useful, and as we go along in this class, we'll learn about various tools that we have to figure out when to use which one. But for now, we're just covering what they are. Now, the last thing we're going to cover before we get to the actual worksheet is destructive versus non-destructive methods. Destructive methods modify the object that was passed in. So an example would be if you passed in some array 1, 2, 3, and the function was called like change 0, I don't know. So you passed it in, and it changes this value to be 0, okay? A destructive method would change the array that you passed in. A lot of the time for destructive methods, the return type is void, right? Because you're editing the array that you pass in, so there's something that you have to return. And even if you did return, you would probably just return the same array. Non-destructive methods, on the other hand, don't modify the object that was passed in. So if you did the same thing with a non-destructive method, instead of, you would pass in this as R, but the return would be a separate array that looks like this. So this array, if you were to access it after this method ran, would look identical to the way it did before, and now you have a pointer to a new array. There are times, again, when destructive methods are more useful. There are times when non-destructive methods are more useful, and we will go over figuring out when to use which as we go along this class. But for this week, all we're focusing on is how to write methods that are destructive and how to write methods that aren't. Great. Okay, let's get started on our worksheet. Just like last week, I am going to start by explaining the problem statement, and then I'll give you a couple seconds where you can pause the video and try to do it by yourself, and then you can all come back and we can talk about it together. I know it's annoying to do the worksheet by yourself, and I know it's going to take more time to do that, but you will learn a lot more if you try to figure out these problems before I just explain them to you. So please, please, please try to do the worksheet on your own. So let's get started with the first problem. So what we're doing right now is we're given this SL list class, which is a singly linked list class with int nodes in it. And we are told to create a function that allows us to insert some item at some position. And of course, there are a couple caveats to this. If position is greater than the length of our list, we just add it to the end. We can assume that position is non-negative, of course, because there's no such thing as a negative position. And we want to create a new int node wherever we add it. And the last thing is we want to do this iteratively and not recursively. A good way to tell that this should be done iteratively is as we traverse through the linked list, if we were going to do this recursively, we would have to have a separate parameter that allows us to pass in where we are in the linked list. Because otherwise, we have no way of keeping track of how far along we are, right? We have no way of being like, okay, this is int node current. We have no way of figuring out which node we visited already. So this is an iterative problem. I'll give you a couple seconds to think about it, and then we'll reconvene and get started. Okay, welcome back. So, I hope you took some time to think about it, and let's talk about the solution. So the first thing that we have to try to figure out is, if we're doing this iteratively, what is the condition? We know there's going to be some sort of while loop, let's say. There's going to be some condition in there, and then we're going to do something. The first question is, how long do we want to iterate through our loop, right? So first, let's have a separate pointer, because we don't have a pointer right now. We don't want to mess with our first pointer, because if we lose the first, we're never getting back because it's singly linked. So let's create a node called current, which points at first, at least, to the first node in our linked list. So how long do we want to keep iterating through our int list? Well, we want to keep iterating until the position equals 0. So while position, let's say, is greater than 1, we can keep iterating, right? In addition, we have another condition. I might have to make this a little bigger. Ooh. Okay, there we go. The other condition that we have is that if we hit the end of our int list, even if position isn't 0 yet, we know that at that point, we're going to want to just add the node, right? Because there's nowhere left to go. But if we allow our current pointer to hit null, and then at that point, we have no way of accessing the node before us, which is what we'll need to connect to the new node. What this means, okay, let me draw it out just so that everyone's clear on this. So if we iterate our cur, right, from here, and then we go here, and then we go here, and then we go to null, which is what this is pointing at, and that's when we stopped iterating through our list, then we have a problem, because once we've done that, if we hit null, there's no way for us to connect whatever new node we create to the linked list that already existed, because we have no way of accessing this element anymore. So this means that we don't want to just go until cur is null. We want to go until cur.next is null. We want to go until we've reached the last element, but not go past that. Okay. So now let's figure out, what are we going to do inside this list? Well, the first thing is, each time we go down, right, we're getting closer to our target position. This means that we should go position minus minus. You can also do position minus equals 1, position equals position minus 1. They're all the same. So we have that. And of course, we want to iterate our current node down by 1 dot next. Okay, great. So we have that logic inside. Now, what do we do once we've hit that position? Once we've hit the node that is behind the node that we want to access? Well, at that point, we want to create a new node, right? We create int node, new node, and then we can do new, I did not give myself enough space to do this, new int node, item, and cur.next. So if cur.next is null, if this is pointing at null, then this will just be null. Otherwise, if for instance we're inserting something here, we want this arrow to point at whatever would be in front of it. We add our item here. And now the last thing we have to do to insert this into the linked list is to redirect to this arrow to instead point at our new node. And so what that means is that we need to do cur.next equals new node. Great, fantastic. This looks almost perfect. There's only one problem. The problem is, what if the goal position is the first one? What if we want to insert it here? So there's a couple extra things you have to think about if we want to do that, right? This first variable is supposed to point toward the very first element of our linked list, which means if we're inserting it at point 0, one thing we have to do is set first equal to our new node. The other thing is, obviously, there's no node before it. So this while loop isn't going to work because we're trying to find something that just doesn't exist. So what we're going to do is create a special condition that's just if position equals 0, or if there are no items in this list, where we call this function, where we call this function add first. And so all we have to do is, we erase that, if first equals null, so if there is no first object, or if position is 0, so if we're adding it at the beginning, then all we're going to do is add first item and then return. So we don't have to do anything else after that. And now that we've done that, that's our solution. Now we've done all of the cases. Great. Okay, let's move on to part 1b. We're dealing with the same singly linked class, and this time what we want to do is recursively remove all nodes that contain a certain item X. And so this is a destructive method, like we talked about before. So the singly linked list that we are operating on will be changed at the end. We're not returning a new list that has these properties. We're changing the list itself. So just an example before I give you some time to think about it, is if you have like 3, 5, 4, 5, and we pass in x equals 5, then the new list, our new list, is going to be just 3 and 4, because we've gotten rid of all the nodes that contain 5. Great, I'll give you a couple seconds to think about it, and then we'll reconvene. Okay, welcome back. Okay, so here we're given these two functions. We're given remove item, and we're given remove item helper. And the reason we're given remove item helper is because we don't want people, oh, and this is supposed to be private. Must have mistyped. Anyway, the reason we're given remove item helper is because we don't want to give outsiders the ability to just call remove item on some subset of our list. Remove item is something that can only be applied to our entire list, not to some section of it. And so we don't give them the ability to figure out which int node we start on. We always start on the first node. And so knowing that, we can tell that what we should do, this returns an int node. So we're going to set that whatever int node gets returned into remove item helper first. And the reason I set first equal to that is, let's say the first node is a 5 in that case above, right? Well, right now, first points to this node. But if we're removing that node, we have to set first equal to whatever else becomes the new first node. So we have to set first equal to whatever gets returned from remove item helper. This will become a little more clear as we do remove item helper. So this is going to be a recursive function. So like I've always talked about, there's two things we have to consider: our base case and our recursive statement. So let's start with the base case. That tends to be easier. So when do we just return something? When do we just return when do we just return a number or some value rather than doing another recursive call in this case? Well, what if current is equal to null? What if we hit the end of this list, right? And we're at this point. Well, there's no operation that we can really do on null anymore. So I guess all we can do is if current equals null, then we just return null. We can also just return current. It does the same thing. Great, so that's out of the way. That's our base case. Once we've hit the end of the list, we just return null and it's over. So now there's two cases we have to think about, right? So the first case is, what if the current node that you're on does have a value of x? So let's say else if current item equals x. Well, in that case, we don't want to attach ourselves to the int list, right? We're going to remove ourselves. So we're going to return remove item helper called on x and current dot next. So it's going to return the rest of our list pass through remove item helper. And then the last case is else, which is also if current item isn't equal to x. And in this case, we want to keep ourselves in the list. So instead of just returning whatever comes out of the calling it on the rest of the list, we're going to set that equal to our next pointer. And so then we call remove item helper. I should have made these names shorter. And then x and current dot next. And then all we have to do is return current. So this covers all three of the possibilities. We're either at the end of the list, or our current node has a value of x, or our current node doesn't have a value of x. If you're not sure whether this works, you have to take the recursive leap of faith and just try out one case, assuming that everything after it works and everything before it works. Does this current case return what you think it will? And the answer is yes. I won't go over it because we have another part to do. Okay, so now we're on to something a little trickier. This is the extra question, so don't worry if you struggle a little bit with this. This is more of an exam level question. So this question asks us to write another method for the SLList class that reverses the elements. So basically, if I have 1, 2, 3, this is going to destructively alter our S-list class to instead be 3, 2, 1. I will give you a couple seconds to think about it. You are not supposed to create any new int node objects. You cannot use the keyword new in this problem. Okay, go ahead. Okay, welcome back. Before we start writing any code, let's talk through this conceptually with this picture and figure out what we want to happen at each iteration. So the first thing we're going to do is, so we have a pointer here that points to first. And in the end, in the goal, we're going to actually have first pointing toward what was previously the last element, right? So we're going to want first to traverse this linked list through over the course of the iterations. So let's say we have first, and then we move it down, and we have first here, and we have first move down here, and eventually point here. Great, that's what we want for first to happen. Now the next thing we have to do, we have to flip all of these arrows. And so how do we do that? So what we actually have to do is have another pointer, because once we've moved first down by 1, now we have no more access to this because it's singly linked, right? But we can't change the pointer that's contained within this node without having a pointer pointing to it as well. So what this means is we'll create a second pointer, we can call it PTR. Here, that first points to the same element as first, and we can iterate pointer, we can have it jump ahead of first, PTR, and now we can keep setting pointer.next to be equal to first. And then after that, we move pointer down by 1, and then we have first move down by 1 as well, and then again we can set pointer.next equal to first. It looks a little messy, but it should be a relatively clean solution. So the first case is, first of all, if there's either no elements in the list or if there's only one element in the list, there's nothing for us to do. There's nothing for our 2 pointers to do. So we can just return. The list is already reversed if there's nothing in it, right? So we'll do if first equals null, or first dot next equals null, return. Done. We can think of this as kind of like a base case. So we have first, and let's create our second pointer now. And we want it to be 1 ahead of first. So we'll set int node PTR is equal to first dot next. Now the node that first is currently pointing to is going to be the very last element of the goal linked list. So we can set first dot next. Now that we have a pointer pointing at first dot next, we don't have to be afraid of losing it. So we can set first dot next equal to null. What am I doing? Equal to null, because it's going to be the end. And at the end of the linked list, there's a null. Okay, so now we can do the actual iteration. So we have while our pointer isn't equal to null. So until we hit this null case at the end, at which case there's nothing to set to anything. First, let's save while our pointer is on this, we're about to set this pointer to point at the previous element, right? But we don't want to lose access to this element over here. So the first thing we have to do before we forget is set some temp int node to be equal to ptr.next. Now that we've done that and we don't have to worry about losing it, we can set ptr, whatever ptr.next currently is, to be equal to first. And then of course now we have to increment both of our pointers. So first has to move down one and pointer has to move down one. So we can set first equal to what pointer currently is. And we can set pointer equal to what temp currently is. And when we do that, we'll keep iterating until pointer hits null, at which point there is nothing left to do in that sense. And we don't actually even have to go in at the end and set first equal to whatever is the last element, because as we've been iterating, once pointer is equal to null, first will be equal to what was previously the last element of the linked list. So this is it. We're done here. Don't worry, this was a little more complicated. It's a harder question than the previous two. Okay, so let's move on to problem 2, which deals with arrays. So the first problem for our arrays problem is we are given an array, an item, and a position, and we want to insert that item at that position. So is it possible to do this destructively first? Is it at all? The answer is no. And that's because arrays, like we talked about before, always have a fixed size. So it's impossible to edit the size of an array destructively. You have to always create a new array to insert an item. So now we have that out of the way, we know this function has to be iterative. So I'll give you a couple of seconds to think about it, and then when we're done, we can reconvene. So the first thing we can do is create our new array, which we know will have a length of 1 plus the previous array. So we'll have int result equals new int r dot length plus 1. Okay, great. So now we have to figure out what position we're going to actually insert this in. Now, if position is less than array.length, this is easy, right? It's just position. But like when we did with the linked list, if position is past the end of the array, we're going to want to insert the item at the end of the array. We can do this with an if statement, of course. We can also do this with math.min. If you worked with Python before, you know that the minimum and maximum functions are just included with Python natively. For Java, you have to import a library called math.min. Again, you can also use an if statement. This is completely not necessary, but it's a good practice of something new. So we can take the minimum of array.length and position. So that's what our actual real position is going to be. Now, for I is equal to 0, I equals some position, we're going to iterate through our original array and copy that over. So this is because up until this position, both arrays are going to be identical. So we can just go for int I equals 0, I is less than position, I plus plus, and then result I equals R I. Now we know that at the position, that our result position is going to be equal to item. And now we have to copy over the second half of our given array over into our result array. And so for this, we will have to start at the position in our old array, because remember, our element, even though we're adding it at position in the new array, there is some element in the old array at that position, so we have to account for that. And we'll go until we hit the end of the old array, I++. And then all we do is result, we're shifting over everything by 1 now, so result I plus 1 is equal to R I. And then we can return result. So there's another way to do this with something called array copy. You can look that up if you're curious, but I won't be covering that today. But it is another acceptable way to do this. I think it's a little more intuitive, which is why I provide this solution versus the other one. Okay, so let's move on to 2b, the very last problem. So for this, we're going to write a non-destructive method again, because again, you can't change the size of arrays, and it's called replicate. So it replaces the number at some index I with Ri copies of itself. So their given example is, we start off with something that looks like 3, 2, 1. It's going to return 3, 3, 3, 2, 2, 1. You can assume that all the elements are positive. So I'll give you a couple seconds to think about it, and then we'll reconvene. Okay, welcome back. So the first thing that we have to do to solve this problem is figure out what the size of our result array is going to be, because we can't add anything or do anything until we have the array already created. So we're actually going to go through the list twice, and the first time we're just going to count how many elements we're going to need. So you can have int total equals 0, and then just for each item, int item. If you haven't seen this syntax before, this is like a Python for each loop, and what it does is it gives you each item in the array inside the variable item. So we're just going to sum up all of the values in array. And now we have the size. Total is going to be the total size of our goal array. So now what we're going to do, is we're going to create our brand new array. Equals new int total. Great. Okay, so we have this array. Should probably put semicolons everywhere. So now what we have to do is we have to iterate again through the items over our original array, and this time put that many of them into our new array. So the way I'm going to do that is a little funky. There's a couple different ways you can structure this. So first of all, I'm going to have an int I that acts as a counter on how far along we are in the new array. So like I will be equal to 0, and then once we're done with the 3's, I will be equal to 3, and it'll be pointing here. And then once we're done with the 2's, I will be equal to 5, and so on. So we have int I outside of the loop. And now for int item R, now we're going to have another for loop that goes from 0 to the value of our item and adds it to the list that many times. So we have int counter equals 0, counter is less than item, counter plus plus, okay. And then we're going to do result. And then, like I said, we have this I here that acts as a counter to keep track of where we are in the result array. So result I equals item, and then I plus plus. And so this will add each item times, and then this will iterate through each of the items to do so. So now that we've done that, we go like that, and we can return result. And that's it. That is the replicate function, and that is the end of this worksheet. If you have any questions, please feel free to ask on Ed, to come to office hours. We love answering conceptual questions. And good luck with the rest of your week.